Geometry is often presented as a list of disconnected equations to be memorized. However, by observing the spatial transition from flat lines to solid objects, we can derive the entire master sheet through logic alone. 2D shapes exist entirely on a flat plane. They possess two dimensions, length and breadth. Because they lack depth, our measurements are limited to the interior area and the perimeter, the boundary wrapping around that area. When we add a vertical z-axis, a flat footprint extrudes into 3D space. This addition of height creates interior volume and an exterior surface area, or the skin of the object. Stretching a shape from 2 dimensions into 3 creates a predictable relationship between the flat base and the resulting volumetric capacity. We will begin the build phase on the 2D plane. Geometry is a multiplicative system. As we expand the dimensions of a shape, the math scales accordingly. A rectangle's area is length times breadth. Perimeter is 2 times L plus B. A diagonal slice creates a right-angled triangle. This interior diagonal length uses the Pythagorean theorem, the square root of L squared plus B squared. When all sides are equal, the rectangle becomes a square. With side A, the area simplifies to A squared, and perimeter to 4 times A. The square's diagonal calculation always results in A multiplied by the square root of 2. Any triangle occupies exactly half of the space of a corresponding rectangle. This makes the area calculation 1/2 multiplied by the base and the height. In an equilateral triangle, where all sides are equal, the height is defined as the square root of 3 over 2 times A, and the area as the square root of 3 over 4 times A squared. For irregular triangles with 3 unequal sides, we use Heron's formula. We first determine the semi-perimeter, S, by adding all sides and dividing by 2. The final area is the square root of S multiplied by the difference between S and each individual side. A parallelogram is a rectangle with slanted sides. Because the vertical distance between the top and bottom remains constant, the area is still calculated as base times height. The rhombus has 4 equal sides. Its area is 1/2 times diagonal 1 multiplied by diagonal 2. A fixed relationship exists here. 4 times the sides squared equals the sum of the squares of both diagonals. For a trapezium, we calculate the area by taking the average of the 2 parallel sides and multiplying by the vertical height. Each of these polygons demonstrates that 2D formulas are simply different ways of quantifying the relationship between flat boundaries and the space they enclose. When straight lines finally become continuous curves in geometry, we must introduce pi, the universal constant ratio of 22/7. A circle's area is pi times radius squared, and circumference is 2 times pi times radius. Slicing it into a semicircle halves the interior space, so the area is simply 1/2 pi r squared. To calculate the perimeter of a semicircle, halving the circumference only accounts for the curve. To enclose the shape, we must also add the straight base, which is 2 times the radius. While curves change the constants we use, the logic of measuring boundaries and interior space remains consistent. Adding a z-axis transforms a flat footprint into a 3D prism. A rectangle pulled upward becomes a cuboid. Its volume is the product of its 3 dimensions, length, breadth, and height. Lateral surface area isolates only the vertical walls. This is calculated as 2 times the height, multiplied by the sum of the length and breadth. Total surface area accounts for the entire exterior by summing the area of all 6 faces. In practical terms, such as painting a room, we calculate the area of 5 walls, the 4 vertical surfaces plus the ceiling. The longest possible straight line inside the box, the main diagonal, is the square root of L squared plus B squared plus H squared. When all 3 dimensions are equal to A, we have a cube. The cube's volume is A cubed. Its lateral area is 4A squared, and its total surface area, the 6 faces combined, is 6A squared. The main diagonal of a cube is consistently side A times the square root of 3. These 3D prisms show how 2D straight-edge math scales when projected into a 3rd dimension. Following the exact same spatial principle, when a flat 2D circle is extruded vertically into the 3rd dimension, it creates a solid cylinder. We find the volume of this cylinder by taking the area of the circular base and multiplying it by the height. The curved surface area is the side wrapper, while the total surface area adds the two circular lids at the top and bottom. A cone represents exactly 1/3 the capacity of a cylinder with the same base and height. To find the surface area of a cone, we must calculate the slant height, L, using the vertical height and the radius. The curved surface area is pi times r times L. Adding the circular base gives the total surface area. A perfect sphere has no flat base at all. Instead, its total internal volume is entirely determined by its radius, 4/3 pi r cubed. Because the shape is uniform, its curved and total surface areas are identical, 4 pi r squared. Slicing the sphere creates a hemisphere with half the volume, 2/3 pi r cubed. The curved surface area is 2 pi r squared, but a solid hemisphere adds 1/3 pi r squared to account for the new flat circular top. Symmetrical curved 3D solids are governed by the radial sweep of a standard 2D circle. We can now apply specific numeric relationships that streamline the transition from raw volume to practical measurement. This includes the conversion of abstract volume into liquid capacity. Every cubic meter of volume equals exactly 1,000 liters of liquid capacity. For any polyhedron, Euler's formula provides a structural rule. The number of faces plus vertices always equals the number of edges plus 2. For calculations involving pi, a radius of 7 leads to a predictable set of outputs. When the radius is 7, the circumference is 44, and the area is 154. Mapping the spatial transition from a flat 2D plane to a 3D solid provides a logical framework for every equation on this master sheet.